Thousands of years before humanity launched the James Webb Space Telescope, our most advanced eye on the cosmos, people were already watching the skies with awe and purpose. Ancient civilizations tracked the motion of stars, planets, and eclipses, not with supercomputers, but with stone monuments, naked eyes, and careful records. They asked the same timeless questions. Where did we come from? What lies beyond? From Babylonian star charts to the observatories of ancient China, from the Mayan calendar to Galileo's telescope, astronomy has always been a bridge between curiosity and technology. Every alignment mapped, every orbit calculated, carried us one step closer to the instruments that now peer 13 billion years into the past. The James Webb Telescope did not emerge in isolation. It is the culmination of humanity's oldest science, shaped by centuries of observation, ambition, and wonder. This is the story of how our search for meaning in the night sky evolved into a machine that can glimpse the dawn of the universe. Long before spacecraft and orbital observatories, humanity's first astronomy was conducted with nothing more than the naked eye. For our ancestors, the night sky was not an abstract curiosity. It was a calendar, a compass, and a storybook written in starlight. In Mesopotamia, some of the earliest written records reveal that Babylonian astronomers, as early as 1800 BCE, were charting the positions of planets and predicting eclipses. They saw the heavens as a system of patterns, measurable and repeatable, and laid the groundwork for mathematical astronomy. Their clay tablets contained data that would later inform Greek theories of celestial motion. Ancient Egyptians aligned temples and pyramids with solstices and stellar risings, particularly that of Sirius, which heralded the flooding of the Nile. This union of architecture and astronomy made the heavens a partner in agriculture and ritual, embedding cosmic cycles into earthly survival. Similarly, the Maya of Central America developed an astonishingly precise calendar system based on planetary cycles, linking their cosmology to both timekeeping and kingship. In ancient China, royal astronomers meticulously recorded eclipses, comets, and novae, treating celestial phenomena as signs that could legitimize or endanger imperial rule. Their star maps, etched on bones and bronze, were among the oldest attempts to systematize the sky. Here, astronomy was both science and statecraft, inseparably bound to authority. Greek thinkers, inheriting Babylonian and Egyptian insights, sought deeper explanations. Pythagoras proposed a cosmos ordered by mathematics. Eudoxus envisioned celestial spheres carrying the stars. Aristotle refined these ideas into a geocentric model that dominated thought for centuries. Yet it was Hipparchus who transformed astronomy into a rigorous science by introducing trigonometry and calculating the precession of the equinoxes. The leap to observation tools came later. In the Islamic Golden Age, scholars like al-Battani and al-Tusi refined astronomical tables with unprecedented accuracy, influencing Copernicus and Renaissance Europe. Their observatories, equipped with massive sextants and astrolabes, were the prototypes of telescopes in philosophy, if not in glass. What these ancient traditions share is an unbroken chain of curiosity. They represent humanity's first recognition that the universe could be measured, predicted, and ultimately understood. The heavens were no longer the realm of divine mystery alone. They became a stage for inquiry. The James Webb Telescope stands as the latest link in this chain. Its golden mirrors may seem far removed from Babylonian tablets or Mayan codices, but the underlying impulse is the same: to decipher the universe by recording light and finding order in its patterns. Before we could launch an infrared observatory a million miles from Earth, we first had to learn how to look up, to ask questions, and to mark the sky with meaning. The story of modern astronomy changed forever in 1609, when Galileo Galilei pointed a small handcrafted telescope toward the heavens. With a simple tube of wood and glass, magnifying only about 20 times, Galileo shattered millennia of assumptions. He observed mountains and craters on the moon, proving it was not a perfect celestial sphere. He discovered 4 moons orbiting Jupiter, undermining the geocentric model. He saw countless stars invisible to the naked eye, suggesting the universe was far vaster than imagined. Galileo's telescope was not the first. Credit for its invention lies with Dutch spectacle makers like Hans Lippershey, but his application of it to the sky ignited the scientific revolution. The telescope became humanity's first true machine for expanding our senses into the cosmos. Johannes Kepler followed, refining the laws of planetary motion through mathematics and theory, proving that orbits were ellipses rather than circles. His insights gave the telescope a new context, not just to see, but to test physical laws. Isaac Newton then advanced the field with the invention of the reflecting telescope in 1668, using mirrors instead of lenses. This innovation eliminated chromatic distortions and paved the way for larger, more powerful instruments. The 18th and 19th centuries brought a wave of breakthroughs. William Herschel built massive telescopes that discovered Uranus, infrared radiation, and thousands of deep sky objects, showing that telescopes were now tools for mapping not just planets but galaxies. Caroline Herschel, his sister and collaborator, became the first woman to discover a comet, reminding us that the expanding reach of astronomy also broadened its participants. By the late 19th century, spectroscopy allowed astronomers to decode the composition of stars, turning telescopes into chemical laboratories. This was revolutionary. Light became data. The realization that every element leaves a unique spectral fingerprint meant telescopes could probe not just where stars were, but what they were made of. The 20th century pushed astronomy above Earth's atmosphere. Telescopes like Edwin Hubble's at Mount Wilson revealed that the Milky Way was not the entire universe, but one galaxy among billions. His observations of redshift confirmed that the cosmos was expanding, forever changing our understanding of origins and destiny. Radio telescopes extended our vision beyond visible light, detecting signals like the cosmic microwave background, a faint afterglow from the Big Bang itself. Then came the leap into space. In 1990, the Hubble Space Telescope was launched, free from the distortions of Earth's atmosphere. At first, plagued by a flawed mirror, it was famously repaired in orbit and soon delivered breathtaking images of nebulae, galaxies, and the earliest structures of the universe. Hubble showed what was possible when instruments transcended Earth's limitations. It became the cultural icon of space astronomy, bridging the gap between scientific precision and public wonder. But Hubble also revealed its limits. Operating mostly in visible and ultraviolet light, it struggled to see through cosmic dust clouds or detect the faint infrared signals from the universe's earliest stars. The dream of a next-generation observatory, one capable of looking deeper into time itself, began to take shape. This was the spark that would lead to the James Webb Space Telescope. From Galileo's crude lenses to Hubble's orbiting observatory, each breakthrough solved one problem while exposing the next frontier. Humanity's instruments grew larger, sharper, and more ambitious, driven by the same questions that had once animated Babylonian stargazers. What is out there? How did it all begin? The James Webb would be built to answer these questions at a scale never before attempted, not just to see farther, but to peer into the very dawn of the universe. The ascent from Galileo's spyglass to the James Webb Space Telescope was not a straight line, but a centuries-long climb marked by bold leaps, technical struggles, and the relentless widening of human perspective. To understand Webb's place in history, we must follow the arc of astronomical innovation, each milestone a rung on the ladder to the stars. After Galileo's revelations, telescopes rapidly improved in size and precision. Johannes Hevelius built observatories atop his own home in Gdansk, creating celestial atlases that mapped hundreds of stars. Isaac Newton's reflecting telescope, introduced mirrors that allowed for larger apertures, setting the blueprint for future giants. By the 1700s, astronomers like William Herschel were constructing massive reflectors, culminating in his discovery of Uranus in 1781, the first planet found since antiquity. His telescopes opened the heavens beyond the familiar solar system. As telescopes grew, so did their capabilities. Joseph Fraunhofer's invention of the spectroscope transformed astronomy into astrophysics, enabling scientists to decode stellar compositions through light. William and Margaret Lindsay Huggins used spectroscopy to determine that stars were made of the same elements as Earth, forging a link between the heavens and our own world. Meanwhile, photography revolutionized data collection, allowing long exposure images that captured faint galaxies invisible to the human eye. Astronomy shifted from artful sketches to precise records, forever changing its rigor. At Mount Wilson Observatory, Edwin Hubble used the 100-inch Hooker telescope to prove that the spiral nebulae were galaxies beyond the Milky Way. His observation of redshift established the expanding universe, a paradigm shift in cosmology. The universe was no longer static or small, it was dynamic, vast, and ancient. Theoretical physics and astronomy converged as Einstein's relativity met Hubble's data, offering the first models of cosmic evolution. The invention of radio telescopes added a new language to astronomy. In 1965, Arno Penzias and Robert Wilson detected the cosmic microwave background, evidence of the Big Bang itself. Ground-based giants like the Arecibo Observatory mapped pulsars and quasars, expanding our knowledge of exotic phenomena. But even the best Earth-based observatories faced an unavoidable limitation: the atmosphere, which blurred and absorbed vast portions of the spectrum. The launch of the Hubble Space Telescope was a watershed. For the first time, humanity had an observatory free of atmospheric distortion, delivering crisp images of nebulae and galaxies. Its deep field image revealed thousands of galaxies in a pinprick of sky, showing the immensity of the cosmos. Hubble also measured the rate of cosmic expansion with unprecedented accuracy, confirming dark energy as a dominant force in the universe. Despite early setbacks, Hubble became a triumph of science and international cooperation, raising both expectations and ambition. By the late 1990s, scientists recognized Hubble's limitations. To glimpse the first galaxies and stars, astronomers needed an infrared observatory capable of penetrating dust clouds and capturing faint, red-shifted light from the universe's earliest epochs. The Next Generation Space Telescope, later renamed the James Webb Space Telescope, JWST, was conceived as the heir to Hubble. Its goals were audacious: to look back 13.5 billion years, to study the atmospheres of exoplanets, and to uncover clues about the origins of galaxies and life itself. Webb's construction was an epic of engineering. Its segmented gold-coated mirror, 6.5 meters across, had to be folded to fit into a rocket. Its tennis court-sized sunshield needed to block heat with the precision of origami. Cost overruns, delays, and technical setbacks made Webb a subject of scrutiny, but perseverance won out. Finally, on December 25, 2021, Webb launched from French Guiana aboard an Ariane 5 rocket. It unfolded flawlessly during its month-long journey to its destination, the second Lagrange point, 1,000,000 miles from Earth. When Webb's first images were released in July 2022, they stunned the world. Nebulae glowed in infrared detail never seen before. Galaxies shimmered at unimaginable distances, their light traveling billions of years to reach us. Webb's instruments also began probing the atmospheres of exoplanets, detecting water vapor, carbon dioxide, and the chemical fingerprints that may hint at habitability. Each phase of astronomy, from Babylonian tablets to Galileo's lens, from Hubble's orbit to Webb's infrared eye, has represented more than a tool. It has represented a widening of perspective. Humanity has gone from asking where the stars are, to what they are made of, to when they were born. The James Webb Space Telescope is not just another milestone. It is the latest summit in a climb that began when humans first looked upward in wonder. When the James Webb Space Telescope, JWST, finally delivered its first images, the reaction was not confined to laboratories or lecture halls. It was a global moment, streamed live, dissected in newsrooms, celebrated in classrooms, and shared across social media feeds. In this instant, astronomy shifted from a specialized pursuit to a mainstream cultural event, a revolution in how humanity perceives itself in relation to the universe. On July 12, 2022, as NASA unveiled Webb's first deep field image, the world collectively gasped. Here was a speck of sky, smaller than a grain of sand at arm's length, filled with thousands of galaxies, some from the universe's infancy. Within hours, the images trended across platforms, from Twitter threads analyzing infrared data to TikTok clips pairing cosmic vistas with music. Unlike Hubble's debut in the 1990s, Webb arrived in the digital age, where information and awe could spread instantly. It became not just a scientific achievement, but a cultural phenomenon. Teachers around the globe rushed to incorporate Webb's images into lessons, using them to spark curiosity about physics, chemistry, and history. Children who had never looked through a telescope were suddenly able to see what the earliest galaxies looked like. For many, Webb's success reframed astronomy not as an elite pursuit of specialists, but as an accessible, inspiring narrative of human achievement. Webb's images did more than impress. They invited participation. Amateur astronomers, digital artists, and educators reinterpreted the data, enhancing colors or layering images to create educational tools. Memes emerged, bridging humor with science, while entire online communities formed around the telescope's discoveries. In a world often fragmented by politics and conflict, Webb offered a unifying vision, the shared heritage of a vast, mysterious cosmos. The telescope's revelations also reignited age-old philosophical and spiritual questions. If galaxies formed only a few 100 million years after the Big Bang, what does that say about humanity's place in the cosmic story? Religious leaders offered sermons weaving Webb's discoveries into theology, framing them as affirmations of creation or evidence of the sublime. Meanwhile, philosophers revisited the cosmic perspective, first popularized by Carl Sagan. The idea that our existence is both infinitesimal and profoundly significant in the context of the universe. Perhaps Webb's most revolutionary cultural impact came from its study of exoplanets. When Webb detected atmospheric water vapor on WASP-96b and carbon dioxide on other distant worlds, headlines around the globe speculated on the possibility of alien life. This was no longer the domain of speculative science fiction. It was data-driven exploration. For the first time, humanity could meaningfully search for biosignatures, chemical hints of life, on planets orbiting other stars. The telescope also became a symbol of what international collaboration could achieve. Built with contributions from NASA, ESA, European Space Agency, and CSA, Canadian Space Agency, Webb stood as a rare example of sustained global cooperation. Its success influenced policymakers to view space exploration not merely as competition, but as an arena for shared progress. Governments that once hesitated to fund basic research saw Webb's impact on public imagination and reconsidered their priorities. Perhaps the most profound societal shift was not in technology, but in perspective. Webb reinforced the sense that science is not just about utility, but about meaning, about the stories we tell ourselves of where we came from and where we are going. By showing us galaxies that formed when the universe was in its infancy, Webb made our own existence feel both fragile and extraordinary. It reminded billions that while our world is turbulent, it is also part of a grand, unfolding cosmic story. In short, the James Webb Space Telescope catalyzed a cultural revolution. It turned astronomy into a shared human experience, reshaping education, inspiring new philosophies, fueling global cooperation, and reviving the eternal question, are we alone? The telescope's societal impact proved that space science is not isolated in observatories and data streams. It is woven into the cultural fabric of humanity itself. In the years since its dazzling debut, the James Webb Space Telescope has settled into its role as the centerpiece of 21st century astronomy. Yet its story did not end with the release of those first breathtaking images. Instead, Webb entered what can be called its working life, an era marked by refinements, diversification of research, and global integration into nearly every corner of space science. Webb's first year demonstrated its raw power, but subsequent years refined that promise into methodical exploration. Scientists no longer asked whether Webb could peer into the early universe. Instead, they asked how far back it could go. Observations revealed galaxies only 300 million years after the Big Bang, a challenge to existing models of cosmology. With every data set, astronomers adjusted theories, recalibrated timelines, and in some cases, rewrote textbooks. Webb became less a camera for cosmic postcards and more a precision instrument, reshaping human knowledge. What distinguishes Webb in the contemporary era is its breadth. Astronomers studying the large-scale structure of the universe share telescope time with planetary scientists examining icy moons and atmospheres in our own solar system. Chemists analyze the infrared spectra of distant exoplanets for water vapor, methane or carbon dioxide, while astrophysicists use Webb to probe star formation regions hidden behind thick clouds of dust. The telescope is not just a single mission, but a platform spanning disciplines, from cosmology to planetary science, from physics to chemistry. The international nature of Webb has also reshaped its governance. Proposals for observation time flood in from universities, research institutes, and even high school collaborations across continents. Teams in South America, Africa, and Asia, historically underrepresented in large-scale astronomy, now participate in analyzing Webb's datasets. The telescope has become a tool not just for elite institutions, but for a truly global community, ensuring that discoveries are not monopolized by a few, but shared across borders. With its success, however, came new ethical and social questions. Webb's data is freely released after a short proprietary period, but debates emerged over how quickly information should be made public. Some argued that immediate release democratizes science. Others worried it undermines the recognition of research teams who worked years on proposals. Another debate centered around cultural context. The telescope's name itself has been contested, with critics pointing to James Webb's role during the mid-20th century and its potential links to discriminatory policies. While NASA upheld the name, the controversy underscored how modern science cannot be separated from questions of history, equity, and inclusivity. Contemporary Webb also faces practical concerns. Though its mirrors and instruments function with remarkable precision, the telescope depends on a finite supply of fuel for orbit corrections. Current estimates suggest it could operate well into the 2040s, a lifespan far beyond original expectations. Still, mission planners must prepare for the day when its fuel runs low. Engineers continue to refine software updates and operational protocols to maximize every ounce of efficiency, extending its life as much as possible. As of today, Webb stands not as a novelty but as the backbone of space observation. Its images of the early cosmos, its detection of complex molecules in exoplanet atmospheres, and its analysis of star nurseries have become reference points for countless academic papers. It is integrated into curricula, documentaries, and public outreach projects worldwide. It has already trained a new generation of astronomers, who will carry forward its legacy long after the telescope itself has gone silent. The contemporary era of Webb then is not about the shock of first discoveries, but about steady, transformative integration into science and society. It is the normalization of wonder, a stage where humanity expects to see galaxies billions of years old, where the chemical signatures of alien atmospheres are no longer unimaginable, and where the boundaries of knowledge expand quietly, relentlessly, every single day. The James Webb Space Telescope is more than just a scientific instrument. It has already become a turning point in the human story. To understand its legacy, we must compare the world of astronomy before Webb with the one it has created today. Before Webb, the Hubble Space Telescope defined our cosmic vision. Its images of galaxies, nebulae, and the deep field became cultural icons. But Webb pushed further, piercing into wavelengths Hubble could not reach, unveiling the very first chapters of cosmic history. It turned what was once speculative, the study of the universe's cosmic dawn, into a data-rich reality. The permanent change lies not only in what Webb revealed, but in how it reshaped expectations. The idea that we can detect molecules in exoplanet atmospheres or witness galaxies forming when the universe was still young is now taken as a given. Webb has normalized the extraordinary, and that is perhaps its greatest legacy. Culturally, Webb reawakened a collective sense of wonder. Its images traveled far beyond the scientific community, circulating on social media, making global headlines, and reigniting public interest in space exploration. For many, Webb's first images were the first time they saw the universe as a living, evolving entity, rather than static dots of light. Webb's legacy also lies in its inspiration. It has become a model for what international collaboration can achieve. NASA, ESA, and CSA united in a project that stretched across decades and overcame setbacks that would have crippled lesser missions. Future megaprojects in science, whether in physics, climate research, or planetary defense, will look to Webb as proof that patience, persistence, and cooperation yield breakthroughs beyond imagination. Finally, Webb serves as a reminder of the fragility of knowledge. Its limited lifespan makes its discoveries all the more urgent and precious. Just as ancient observatories left their mark on history, Webb ensures that this generation, too, will be remembered as one that dared to look farther and deeper than ever before. The telescope's legacy is not only scientific, but philosophical. It changes how humanity sees itself, a small species on a small planet, yet capable of building a machine that captures light from the birth of time. What comes after Webb? That question now drives the frontier of astronomy. Webb has opened a window onto the early universe, but like every great instrument, it also raised new mysteries. Galaxies that seem too massive too early challenge current cosmological models. Exoplanet studies revealed chemical signatures that demand more sensitive instruments to confirm. The future of space observation will be about addressing the puzzles Webb exposed. One clear direction is the search for life. Missions like the upcoming Habitable Worlds Observatory are being designed to follow Webb's lead, targeting Earth-like planets around Sun-like stars with direct imaging. Scientists imagine not just detecting atmospheric gases, but spotting biosignatures, chemical imbalances that may hint at biology. Webb has laid the groundwork, but the next generation of telescopes will sharpen the focus. Another frontier is scale. If Webb is a 6.5-meter mirror at Lagrange point 2, future designs imagine even larger segmented mirrors, or fleets of smaller telescopes working together in formation, creating a virtual observatory spanning thousands of kilometers. Such concepts could provide imaging sharp enough to map continents and weather systems on exoplanets. Technology will evolve too. New materials, autonomous servicing robots, and on-orbit assembly may overcome Webb's biggest limitation, its finite fuel and distance from Earth. Unlike Hubble, Webb cannot be repaired by astronauts. But future telescopes might be built to self-correct or even grow over time. Speculation also extends beyond astronomy. Webb's success has reinforced the value of big science, massive collaborative projects that unite nations in pursuit of knowledge. Could the model used for Webb inspire global efforts in climate engineering, asteroid defense, or quantum computing? The telescope may be less a final step than a blueprint for solving humanity's greatest challenges. And then comes the philosophical question. What if Webb, or its successors, finally detect unmistakable signs of life? How will humanity respond culturally, religiously, politically? These are questions no telescope alone can answer, but Webb ensures we must begin asking them. In this sense, Webb is not the end of a story, but the beginning of one. It reminds us that discovery is infinite, and that with every mirror we launch into the void, we uncover not just the universe, but ourselves. From ancient skywatchers tracing constellations with the naked eye, to medieval scholars mapping celestial mechanics, to engineers unfolding the James Webb Telescope a million miles from Earth, humanity's gaze has never wavered from the heavens. The Webb Telescope is not just a triumph of technology. It is the latest chapter in a story that began thousands of years ago with simple questions under the night sky. It reminds us that curiosity drives progress, that wonder fuels innovation, and that every generation inherits the dreams of those who came before. Webb does more than capture light from ancient galaxies. It illuminates the enduring human desire to know where we came from and where we are going. If this journey through the history of astronomy inspired you, then help us keep telling these stories. Like this video, share it with others, comment with your thoughts, and subscribe for more deep dives into history and innovation.